Greetings everyone, my name is Flora Sergio and I'm a forest engineer from Forest Design. In today's video I'm gonna show you the workflow for measuring wood piles using the FJD Trion S2 LiDAR scanner and the Forest Design wood pile analyzer script that we made specifically for this purpose. As an introductory, we at Forest Design, our motto is the nature in digital format, and lately the FJ Dynamics scanners did a great job for us in improving our data and also data collection and the results. In today's workflow, we're gonna go to the steps that we did from getting the raw data until the results. As you can see here, the case study is focused on a lumberyard where we want to extract all of the wood pile and then have an overall look on the measurements and the results of the whole lumberyard. The first step, as in any scanning process, is to go in the field and just scan the point of interest. In this case, we have the lumberyard. And I'm gonna show you here the images that we extracted from the FJ Dynamics, the P1. So in this video, we use the P1 scanner to measure the whole lumberyard. Then you can see here, it's my colleague Bogdan. You may know him from other videos. He just did the scanning. And actually, this being a bigger lumberyard, we were forced to do it in 3 separate scans. You can see here all of the wood piles, and you can see the difficulty in measuring the volume in those, being that they are so irregular. But as a first step, you have to get the data, and this moves on to the second step. So after we got the raw data from the field, and the nice part about the LiDAR scanners is that this step one can be done by everyone, so it is not needed for you to go personally there to scan the point of interest. You just anyone can do it. Actually, from our experience, we used other scanners in the past, and all of them they had the same problem. If you were not careful enough on the way that you plan your trajectory, it was a big possibility for the scan to be corrupted, and then the data is not useful. You can do anything with it, and you are needed to redo the scan. But actually, on the FJ Dynamics scanner, we found a pleasant surprise that even if you don't have like a big plan ahead on the path, the algorithm managed to get a really good data out of the scanner, no matter the path that you choose. Moving forward, after we got the scans from the field, we use the queue processing for getting the raw data from the LiDAR scanner into LAS point clouds. And as a side note here, we are now doing some monitoring plots in a forest. We have like a big grid over a very big surface, and we would like a wish list to be able to process the raw data from the scanner via command line. So we were not limited by the 10 scans that we have to use in the Trion model. But I'm sure the team maybe will take this into consideration, and who knows, in future updates this will be a possibility. Moving forward with our case study, we have the point clouds here. This is the lumberyard. After we did the processing, the mapping part, we also did the colorization, and the application, the Trion model, is really nice because in this case, even if in the field the operator didn't use the GNSS options of the scanner, and point clouds now are overlapping, I actually can, based on the reference one with the registration option from here, I can match the more scan separately. So you can see I did this already in this part. So you can see this is a colorized point cloud. This is the first scan with the trajectory that my colleague choose for this. And this is the second one, which actually merged perfectly with the first one. Even if the Trion model is an amazing application, I'm not gonna bore you that with all the technical stuff. So I already did the lumberyard. You can see it here. All the 3 point clouds are registered together. So now we have a really big yard merged. And from this point, you can see all the wood piles. So moving forward, we cropped 2 piles that we wanted to furthermore put them in the wood pile analyzer. So we have this plot here, this pile. So we're gonna call it pile 1 and pile 2. That is the wood pile analyzer. So this is open source, is made by us, and by request you can send us an email and we'll send it to you. So it's really neat and easy to understand the interface. So we have the last file input here. I'll hit the browse. I have already made the folder with the executable here, the inputs and outputs. So for inputs, I want to put firstly the pile 1, which is this one over here. We can recheck it on the Trion model application. And also the output folder, which I want to be in the outputs here. So we have a number of analysis parameters. I like to mostly let them on auto. And we also have some control parameters that we want them to be like really specific. In this case, we have the log length, which I want to set at 3.2. This means that the algorithm will calculate the log length from the point cloud, but also made a separate calculation with the length that I put here, in this case the 3.2 meters. Because it's common practice that if the mill wants a 3-meter log, you have to deliver with an overlength, because if they do not have that overlength, usually it's like 10 or 20 centimeters, there is a risk that your wood will be declassified to the next length. So in this case, if you don't deliver like for a 3-meter requirement, 3.2 meters, it is possible that the factory will say, okay, I will pay you not 3 meters, I will pay you 2 meters and 70 or something like that. Moving forward with the parameters, I would also like to modify this one, the profile corridor, because the algorithm makes a profile corridor, as it said, on the stack faces. So I can look here in the point cloud, because it is also colorized and it's really neat to see. I can see that the faces here are not exact, so they are not stacked pretty well, and I would like to modify this instead of 0.25 to be 0.5, and just hit the run analysis button and wait for the results. So I have this output folder in which all of the results on the pile should be done. When I see this one, I can see that the analysis is finished. So we have a number of images. The first one is the raw view, the raw above view of the point cloud. This one is the profile, so it's a lateral picture of the stack. You can see here the estimated ground and the upper pile profile. In this case, the platform was on really level ground, so we don't have problems in the estimating which is the ground is. Also another lateral profile picture, and on the above view here we can see the edges and the sections that the algorithm made to generate the faces of the logs and do the calculations for the results. So we have the center line, the right and left longitudinal profile, which basically based on those lines these pictures are generated. I can see that in this case the algorithm didn't specifically end here as the last log and continued forward. So if this happens, we can modify here. So I have the draw axis button here and I can redo the center lines. So this is the center line. Now we have this one. We can also make it from multiple points, and the purpose of this is to hit each log in the stack because they are not stacked very well, and you have like different faces coming out, and those can cause errors. So before we run again the analysis, we can see the report here, which is the results. And I'm curious to see if the stacking factor is changing because this is automatically calculated and doesn't depend on the axis here. Only the gross pile volume depends on here. So now we have 91 with a stacking factor of 77. This is the gross pile volume, and the interest is the 64 here. So if we rerun the analysis, we should see different results, and also these two longitudinal profiles should change because you can see this gap here and this gap in this part. They shouldn't be any gaps. So this is much better now. You can see the estimated ground remain really flat and the upper pile profile modified a little bit depending on the profile that it sees. So let's see if the results change. So now we have a really better result, but the stacking factor remained the same, which is our main focus because we wanted to calculate automatically stacking factor, and uh, this is really important that no matter how the lines are drawn, the stacking factor should be the same because the empty spaces in the wood doesn't change. So this is really important to be the same. So regarding the results, we have the PDF file which compiles all of the data that we need regarding those wood piles. So we have the summary with the pile length of 9 meters, the pile width of 3.79, the maximum pile height 2.7, average pile height 1.6, and the important part, we have the gross pile volume. This means also the empty gaps in it of 75 cubic meters. Now we apply the stacking factor and we have here two values. One is the auto stacking factor and one is the manual coefficient that we manually put it in the analyzer. So you can see the differences here. They are not so big because the stacking factor is actually not really far from the what we put it. The estimated log count, and of course the images. You can see here the longitudinal profile lines that we draw. You have here again the same pictures in the output folder and the faces of the stack. In conclusion, this workflow has three main steps. The first one is the field scan, where we capture the wood piles in the yard. The second one is by using the Trion model application, we converted the field data into the 3D spatial data. So in the end, we were able to analyze the pile and generate the results using the wood pile analyzer. In the end, I would like to say that this is the open source file, so just email me at the email on the screen and I can send it to you. As a side note, I want to say that a few years ago this wasn't possible. So I can say thank you to FJ Dynamics scanners that they really do a great job, and we hope that we can use them in the future as well. Thank you for your attention.